Yeah, so you could have a different number of column vectors as there are elements in the vectors. Is that what you're saying? Oh, yeah. Yeah, so these, yeah. So the ends here have to match. And if we're allowing it to not match, we usually would call it a different letter like M or P or something. Yes, this has to match to be able to do the multiplication. All right, let's do an example. I think I have an example. I had an example ready last time, but we didn't work on it. So here's our example. And what we could do is we can translate this into the system, make it look like a system of linear equations, or we can just go ahead and try to solve for it like um, what we do when we row reduce. So let's just go ahead and do that. So our augmented matrix is going to be 1, 2, 1, -3, -1, 2, 0, 5, 3, and then we're going to augment it with B. So this is like A1, A2, A3, and B. And what we want to do is we want to row reduce this to see if we can get any solutions. So I think for there's already a 0 there, that's good. I think I want to multiply the first row by 3 and add it to the second row. And so everything will stay the same except the second row, and that will make the first element equal to 0 because that's what we had intended to do. And we got 3 times 2 is 6, 6 minus 1 is 5, 3 times 1 is 3, 3 plus 2 is 5, and 1. Okay, so now we can, I think I could just multiply row 2 by -1 and add that to row 3, and then that would get rid of that 5. So I would have 1, 2, 1, 0, 0, 5, 5, 1, and 0, 0, and then 5 times -1 is -5, plus 3 is -2, and -1, -1, -2. So does it seem like we have a consistent system? Yeah, we have at least one solution. Do we have more than one solution? Do we have a free variable? We don't have a free variable, so I don't think we're going to have more than one solution. So I think we're going to have exactly one solution. We can continue to row reduce this, but I don't have a calculator, so I'm not going to. Actually, I do, but still not going to. So you can rewrite this as back into the equation. We have -2x3 is equal to -2. So that gives us a solution for x3. So this part is called back solving. I don't know if we ever defined that. So the next one we have a 5x2 plus 5x3 is equal to 1. We know that x3 is equal to 1. And so we're just going to solve for this x3 or x2. This is a 2. So 5x2 is equal to 1 minus 5 is negative 4. X2 is equal to negative 4 over 5. Yeah. And then the last one, we have x1 plus 2x2 plus x3 is equal to 0. So let's put in those values. We got negative 4/5 for x2 and 1 for x3. What is it? 3 over 5. Okay. So we went and yeah. There's only one. There's one unique solution because one, we didn't have any free variables. A free variable will give us an infinite number of solutions. Two, our last row, when we got it to reduced, when we got to row echelon form, it didn't have a set of zeros with a non-zero on the last part. So remember, your key things to look for, if you have your row reduced or row echelon form, if your row echelon form has looks like this, where it is zeros and then your augmented part is non-zero, then you have no solution. And if your row echelon form has a free variable, then you get many solutions. And then in our case, we have something that's not 000b, or that doesn't have any free variables, so we have a unique solution. Those are like quick keys to look for when you're trying to solve, after a row reduction. It should give you hints as to what kind of solutions you should get, right? I think it's because your stairs look like this and there's not any extension for one of them. And usually, what's the definition of a free variable? It's the one that's not free. So you look for the pivot columns, and there's a pivot column in every column. So there's a pivot element in every column. Yeah, the staircase goes down. Chris? Yeah. Whoops. Yeah, if we were to keep going with this, that's exactly what would happen, is that these things would become ones, and then you would have zeros. So in fact, now that we know the solutions, we should know the row reduced form of this. Yes, the arrow doesn't belong there. And this is like an afterthought. By the way, the reduced row echelon form is going to look like this. It's going to have to be like zeros and ones, and then the last row or the last column would be the solution, right? So we got x3 is equal to 1, x2 is equal to negative 4/5, and then x1 is equal to 3/5. Okay, if we were to go all the way with our row reducing, we would have eventually gotten this. Okay. So there's you guys heard of MATLAB? Does anybody have MATLAB? Yeah. Is that what your question's about? What was your question about? Uh-huh. No, it's not free. I don't know. Yeah, I'll show you guys a couple more things. $50 for what? Anyways, we can create a matrix kind of easily, and then RREF, I think. With one quick command call, you have the solutions. What? So, while we're in the topic, no, not if you downloaded it. You guys have a special assignment. It's not so special, it's just a worksheet where you have to download either MATLAB, if you want to pay for it, FreeMat, which is free, or Octave, which is free, and walk through some commands from a worksheet. Oh, it doesn't have a link yet. Let's put the link for the worksheet. So there's a worksheet for you. There's slight differences. I think Octave looks a little bit more like MATLAB. So I guess if you're on the fence between them, I would maybe plug for Octave a little bit more, because it keeps track of the file system a little bit better than MATLAB. And so the worksheet that you would be looking at would give you a little bit of a, oh man, it's downloaded. Would give you some basic commands on how to write vectors and how to write matrices, how to figure out the size of things, and just a handful of commands that would get you started with being able to use MATLAB as a calculator for this particular class. And then towards the end, there are problems for you to try to do, which should be pretty straightforward after you've gone through the quick lesson. And we'll do more of this. I'll make more videos. I won't spend too much class time on it because I expect you to do it outside of class. But I'll try to provide videos for certain things as needed. but I think the commands that you would be copying down would be pretty straightforward on your Octave or FreeMat or whatever it is you're using. And if you're a computer science person, I'm going to have a few challenge problems for you to try to do, and that's to create some functions that would help row reduce, because RREF, that particular command, reduces directly to the reduced row echelon form. But if you're interested in seeing the steps, you know, you have 3 basic row operations. You can swap a row, you can scale a row, or you can multiply something by a row and add it to the other and replace it. So those 3 basic row reduction, what's it called? Row operations, thanks. So those 3 basic row operations can be set as functions with, you know, certain parameters, and then you can reduce it. All right? Yes? Oh, I fixed it. Any other comments? Is there a comment? All right. So this will give me a reason to pop up MATLAB every once in a while in class, so I don't have to row reduce anymore. When is it? Oh, yeah. A week from today. The only thing is that the row reduction here, you know, because this is a calculator, it breaks everything up into decimals, and so once in a while I might use Wolfram Alpha to do the row reduction, and then that'll get us staying in our fraction looking things.
What would that command do if you tried to apply it to a matrix that was not able to be put in that form? Like if there were free variables, obviously.
Oh, yeah, if they're free variables, then it'll just look like they're free variables. So let's say A equals 1, 2, 3, 4, 5, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5. And so you would just like have a row of zeros, or have something with zeros and ones in the bottom or something like that. So there's a process, there's an algorithm for this where you're going to get a unique answer every time. And just something like this would be an example where there's a couple of free variables in row 3 and row 4, and so we would have an infinite number of solutions for this problem. All right, let's go back to our business. So this is really just taking this matrix equation that they're introducing and then saying it's really all the same thing. It's just exactly what we've been doing. And pretty much everything that we're going to do for the next couple of days will be pretty much everything that we've been doing already. And so starting tomorrow or on Wednesday, we'll take a look at linear independence, which has like a name to it, but we're going to be doing row reduction and finding solutions and stuff like that. Yeah. Yeah, the solution set can be seen as a vector. So we can identify our solutions in this box, in these red boxes. That's one way to think about it. We can also say that our solution, x, and remember the bar over, or the arrow over a variable means it's like boldface and it's a vector. This is equal to 3/5, -4/5, and 1, which is a vector. So that's another way to state this solution. Say x1, x2, and x3 equals 3/5, -4/5, and 1. So there's many ways to state our solution, and unless I specify how I want the solution written, then you can, writing it like this would be fine with x1 equals this and then x2 equals that. But soon enough, we'll be taking a look at vector forms or parametric forms of equations, and those usually tend to have free variables involved, and so we're gonna want our solution written in a specific way. Okay. So next is a theorem that kind of says what we've been saying all along. That says that we're translating this equation ax plus b, ax is equal to b now as like an inspection of linear combinations of a set of vectors. So equation has a solution if and only if the linear combination b is a linear combination of the columns of A. So that's a way we can make our connection with linear combinations now. And then just to tack on a theorem, if you have an M by N matrix, then these four things are equivalent, which is to say that they're either all true or all false. The first one says the equation has a solution for each value of the vector b, or for each vector b. Also, we can write b as a linear combination of the columns of A, regardless of what b we choose again. And then the next one says the columns of A span Rm. The columns span this m-dimensional space. And then we have a pivot in every row, pivot position in every row, which is to say that there's no free variables. Now that means it's consistent, that we have a solution. I'm thinking if n might be longer or larger, so we might have free variables. So maybe we'll scrap that free variable comment. All right, let's do number 15. And this one says, let A equal to, maybe I don't know if we're going to do number 16, but let's do number 15 for now. So we have a 2 by 2 matrix, and B1, B2 show that the equation does not have a solution for all possible B. And then describe the set of all B for which AX equals B does have a solution. Okay, so I think the task here, well, in terms of solutions for AX is equal to B, we're trying to show them that there's probably going to be a certain value or a certain set of values for B1 and B2 where this thing's not going to have a solution. And then there's going to be certain values for B1 and B2 that will have a solution. So we're going to see if we can catch that and figure it out and then translate it back from an equation to the idea of, what was the first thing that was said? The idea of a linear combination and the idea of this being spanned. So let's get to it. Just set it up like an augmented matrix. And then do the row reduction. So I think I want to multiply the first one by 3, add it to the second row. So if I multiply the first one by 3, I'm going to get 3, negative 3 added to 3, that's 0. And then I have B2 plus 3B1. So this is my my solution. So we see, let's see, show that the equation AX equals B does not have a solution for all possible values of the vector B. And we see that as long as this term is not 0, then we have no solution. As long as this is non-zero, we have no solution. And they say for any random variables for B1 and B2, so it seems like if I pick B1 equal to 5 and B2 equal to 7, then this is not going to work. And so we have a bunch of vectors that's not going to have a solution for this. However, we do have some possible solutions for this. I wanted green. If what? So we do have solutions for this if B2 plus 3B1 is equal to 0. So if this is equal to 0, then what do we have? Solutions. Then we have many solutions. That's better than writing an infinite number of solutions. We have many solutions. Yeah, because you can let it be one, be whatever you want. So we have many solutions if this is the case. What does this mean? Let's see. If the equation has a solution, it doesn't say anything if the equation, but this one, the equation has a solution for a specific b, but it's not for each b that we have. So according to this problem, the first one is false. The first statement here, each b in Rm, the equation has a solution. That's not true because there's a lot of b's in R2 that doesn't have a solution. So that means everything else is false. So what's false? It means each b is a linear combination of all the columns of A. That's false. The columns of A span all of R2. M is equal to 2 in this case. That's false. And then A has a pivot position in every row. That's false. In every row. So there's a pivot here, but there's no pivot here because that's a 0. Pivot is non-zero. So M is equal to 2. I guess this should be in red. That doesn't matter. So the columns of A are 2, negative 6, and negative 1, 3. Right, so these are the columns of A. So that says that columns of A do not span all of R2. So that means we can find a vector in R2 that's not a linear combination of these things, right? And we can find that by just randomly choosing B1 and B2 so that this this expression B2 plus 3B1 does not equal to 0. I don't know. Are they the same vector? So these two look like they're the same vector, scaled. Well, if you can find a number where this wouldn't have a pivot or this wouldn't have a solution, then you can just say, according to this theorem, then it doesn't span all of R2. According to the theorem, based on these things. But your observation, we'll talk about your observation in a minute. So, Brian. And then, yeah, or if it satisfies any one of these four things, then it would satisfy this, which is spanning all of R, whatever. So back to Delilah's comment. So it looks like she might have noticed that these two are collinear, scalar multiples of another, right? They're parallel. So these vectors are parallel, which means they don't fall apart or they don't come apart to be able to span all of R2. They just span a line. So note that these vectors are collinear and span a line, and not all of our R2. Do you know what this line looks like, by the way? I meant, can you give me the equation of the line, by the way? Say it again. Slope is minus 1 over 3. It goes to the origin, so that's all we need, right? Well, with slope, we usually say y equals mx plus b. So is this what you meant? I don't know. Why do we know that? So when we're talking about spans, we're talking about a linear combination of vectors, right? And we're talking about linear combinations of vectors. They're always spanning from 0. Is this right? Negative 3x? Yeah, yeah. So another way to try to get this equation is to take a look at your solution or your possible solution. So let's try to, in the second part of this question, describe the set of all b's for which this has a solution. So we can write this equation, so as long as it satisfies this equation, but our b, let's pretend that we can write it as x and y. And then so that means b1 is equal to x and b2 is equal to y. So if we write this equation in terms of x and y, and we have that exact line that we're talking about, right? Now draw this line, draw these vectors. You see that those vectors are going to be on that line. Okay, and any linear combination of these vectors will remain on that line. So in 2 dimensions, it's easy to study. It's kind of easy to figure out the different scenarios that we would have if we have 2 by 2 matrices. When you look at 3 dimensions, if you have a good visual or a good memory of what happened in Calc 2 or Calc 3, where we're talking about lines and planes, then you can still try to visualize that. But anything beyond that, it's going to be all theoretical because we can't see it. Unless you imagine it and get some other foreign substances in your brain to help you visualize 3 dimensions, 4 dimensions, 5 dimensions. It's legal now. For simple graphs in 4 dimensions, so cubes. Yeah. You can use color, you can use thickness of pencil. Yeah, you can use a bunch of things. All right. So let's continue talking about systems and matrix equations, and then continue to relate it to the idea of spanning and things like that. So homogeneous, I got used to when I was in college, homogeneous, but let's say homogeneous. I'll try to say homogeneous. Well, I don't think it works like that. So the idea of homogeneous is something just is equal to 0. There's this unfortunate definition in differential equations where they talk about homogeneous differential equations that doesn't really fall under this category. And then later on, they'll talk about homogeneous differential equations that does fall into this category. So it gets a little confusing. So if you're in the differential equations class tomorrow, we're actually going to talk about homogeneous differential equations, but it doesn't mean this. So a homogeneous system just means that your matrix equation form is going to say AX is equal to 0 instead of AX is equal to B. And we have to note that 0 is the 0 matrix or 0 vector. I forgot to change this into a all right. So to make things really easy, we know one solution right off the bat. 0, right? If all the components of x is equal to 0, everything's going to be 0. So that 0 is called the trivial solution. That's the easy solution. And it's always going to be a solution. What we're interested in is trying to figure out the non-trivial solutions. And we have some sort of a key as to when we would have a non-trivial solution. It says here, a homogeneous system is going to have a non-trivial solution if and only if the equation has at least one free variable. So this is where we get our free variable business. It's going to help us. All right. So we have an example down here, x1 minus 3x2. I'm just going to plug that into my sophisticated calculator. So that's 1 minus 3, 7. And I could put 0 here, but it's really not necessary since it's a homogeneous differential equation. We know that the last element's going to be 0. I have a minus 2, 1, minus 4, and I think we're putting the zeros in, a 1, 2, and a 9. And let's go ahead and row reduce that, and we get this. That's kind of boring. So anyways, row reduce it, we have no free variables here, right? What's the solution? 0, 0, 0. So this gives us, well, first of all, based on the statement over here, if it has at least one free variable, then we have a non-trivial solution. Here we have no free variables, pivots and everything. So then we only have one solution. And that's going to be 0, 0, 0, the trivial solution. Wow, our examples are going to go a lot faster with MATLAB. Yeah. Oh, yeah. I feel like maybe we should do another example. Let's do. Let's do one where we're actually going to get a solution. So here's our next example. And go ahead and use MATLAB again. One, 3, 1. Minus 4, minus 9, 2. And there's a 0 for the last row, right? And then minus 3 and minus 6. So in this particular scenario now, we have, we don't have that nice ones in the diagonal, kind of left one out. So let's take a look at what we have. What we have is a free variable in x3, right? So that means we can write our solution in a variety of different ways. I think we've only written our solutions with x3s and x whatever the free variable is. So let's go ahead and try to get our solution written here. The second row, from row 2, we have x2 plus 2x3 is equal to 0. So x2 is equal to negative 2x3. After we noticed that x3 was free. And then x1 minus 5x3 is equal to 0. So that gives us x1 is equal to positive 5x3. Yeah.
Based on that idea that x3 is free, or are those not terms?
People don't usually use the term independent variable, although it might be okay. Usually we think of independent variables as functions, and we're not really dealing with functions here. Although we can. Did I make things more vague? I'm just here to put a cloud over you. So you can write your answer like this, but more often than not, if you have a free variable, I'm going to want you to write it in another form. And the form that we're going to do is we're going to try to write your x as a solution where it can be written as a 5x3 is my first component x1, my second component x2 is negative 2x3, and then my third component is free, so I will just write x3. And I think I might have done this already before, but we can write this as 5, negative 2, and 1, because they are all multiples of x3, and you know when you multiply a vector by a scalar, you distribute it to all the components, and so we can write it in factored form. I don't know if we would call it factor form, but you can write it like this. This would be written in what's called parametric form. And you can actually go one step farther over here in parametric form and write your x is 5, negative 2, 1 with an actual parameter as we know of as a parameter. Now, with Chris's comment about this being an independent variable, now we can see this as an independent variable. And just for fun, we can see how this looks like as a function. Of t. So if you've studied parametric equations, this is a parametric function in 3 variables. And if you were to look at it, it's this line. This line is a line that spans from 0 to 1. So if we want to make it go longer, you can say minus 2 to 5 or something like that. And now you have a longer line. And the parameter t tells you x3, that number x3, it can be seen as a parameter t, tells you when to start and stop. In fact, you can look this as a pointer, a vector. Yeah, it's scaled by t. So we have a vector solution, so to speak, and then we're scaling it by t. I'm just wasting time now. All right, so it's really just a parameter, and in that sense, you can call it an independent variable. It's a free variable. Okay. So parametric form. Sometimes they call it vector form, but this value over here, this is the important vector that you want to look at. So what you're saying is that the solution is spanned by this vector. So to say that means that any solution that would work for this system that we're looking at up here is a linear combination of this vector. Well, a linear combination of one vector just means you get to scale that vector to whatever you want. If you had two vectors, then a linear combination of two vectors would be something else. But in this particular problem, we only have one free variable, and that one free variable is associated with one vector, and that one vector spans your solution. Yeah. Which is just a line in R3 in this particular case. There I go. Just waste. How much time did we waste? We wasted about 5 minutes on that graph. I suppose we still have 3 minutes left. Oh, solutions to non-homogeneous differential, or not differential equations. Yeah, we'll put this up next time. Next time we're going to finish 1.5, and then we're going to finish with non-homogeneous systems, and then look at the relationship between homogeneous and non-homogeneous systems. And in R2 and R3, we can see it graphically. So we'll do that.